All righty then. So we have talked about in the last two lectures about the definitions of derivatives. We talked about where there could be a lack of differentiability. Well, now comes the exciting lecture, the one we call shortcuts, one where we don't, we're building towards not having to use the definition of the derivative every time we want to find a derivative. And so this lecture is all dedicated to saying, hey, is there some way to find derivatives that's faster than using the limit definition? So we're going to have a bunch of rules. Rule number one is called the constant rule. It says, hey, if I have a function which is a constant function, I mean, this is like f of x is equal to 3, or f of x is equal to pi. F of x is equal to just some constant. Well, then the derivative of that function, the derivative of the constant, is simply 0. Now, one way to look at this would be to think about, well, what does f of x equals 3 look like? Well, you go to 3, and there's your line. And yep, that line definitely has a slope of 0. And it could be at 3, could be at pi, either way, slope of 0. But let's go back to the definition and let's actually prove that this is true. So let's go back and say, okay, the definition of the derivative is, again, f prime is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Now, in this case, f is some constant. So the limit as x approaches 0, well, the minus part is that constant. But what about f of x plus h? It is also that constant. So we end up with the limit as h approaches 0 of 0 over h. Now, what is that limit? Let's imagine this function. Here's our axes. This function is 0 everywhere except an undefined at 0. And I think we can tell that as we approach 0 from either side, that function gives off a 0. So this limit is just 0. And so we have proved it. Okay, so what does that mean? That means when you hit this problem, hey, what's f prime if f of x is equal to 4? You don't need to go and do the limit definition anymore. You can just say, oh, I know the derivative of a constant is 0. And you're done, because we've proved it for in the most general sense. All right. That's called the constant rule. Well, what about this thing called the power rule? The power rule. It says, if you have something in the form of the function of x is x to the n, and by the way, n has to be a positive integer, like x cubed, for example. It says, to take that derivative, you can bring the power that used to be there, bring it down, and reduce the power by 1. But again, that's the rule. We're not allowed to use that rule until we prove it. So let's prove it. Here's how this proof goes. So you start with the limit as h approaches 0, again, of f of x plus h minus f of x all over h. Good thing I memorized that. And again, our function is x to the nth. So when we put that function into our definition, we get x plus h to the nth minus x to the nth all over h. All right? And you say, okay, what does that look like when we expand it? Well, you may or may not have done in pre-calculus something called the binomial theorem. But it says when you expand some binomial, like x plus h, to some power, the first term is x to the nth. The second term always ends up being n, x to the n minus 1 times h. And then there's a bunch of other terms until it finishes up with the last term, which is h to the nth. Okay, I'm not going into the binomial theorem, but I am about that binomial theorem. I am teaming with a lot of news. All right, and what's at the end of this? X to the nth. And this is all over H. Now, what we'd like to have happen is we'd like to have some nice cancellations. Well, how about this cancellation? This X to the nth and that X to the nth cancel. That's a nice cancellation. And when we go down to the next line, we might notice that in every term that remains, this one starts with an H, this next one will also have an H, all of the other terms have H's. So I can factor that H out, and I get n x to the n minus 1, and the only H is there. And then all the other terms have H's, but they're reduced by 1 power. So that's H to the n minus 1 at the tail end there. And that's all over H. And we really like that because it allows us to cancel out those H's, which means the only thing that's keeping us from applying the limit has now been taken care of. All the terms that remain, although they have one fewer H than they used to have, they all have H's, which means when I apply the limit, everything goes away in this circle, and the only thing that remains is n times x to the n minus 1, which is the rule that we wanted to follow. So what does this mean for us? Hey, instead of using the definition, we can now say the derivative of x cubed, that is, bring the power down 3, and then reduce the power by 1. How about, what if f of x was equal to x to the 7th? Well, then that derivative is bring the power down and reduce the power by 1. Super easy. And that's called power rule, at least for positive integer powers. All right. Next rule, the constant multiplier rule. It says, let's say you have some function that's in the form of some constant times some function. The derivative of that function, that derivative of that constant times a function, is pull the constant out and then multiply by the derivative of that function. In other words, the constant multiplier can be set aside and then deal with what remains. Okay, again, let's not just take my word for it. Let's prove it. The limit as h approaches 0, in this case of c of x plus h minus c times f of x, all over h. Okay, so I just use this definition, and that definition shows up here, and then that definition evaluated at x plus h is right there. Well, it seems to me what I see is that both of the terms in the numerator both have a c. So how about I just factor that out? I can do that. Can I? I didn't break any laws of algebra there. That's great. Well, you know what? This c doesn't have any h's in it. It's not affected by the limit at all. I could go so far as to pull the c all the way outside the limit. And when I do that, what I see is this thing is the very definition of the derivative of f. And so I've now proved it, that you have a constant multiplier. What you get is that constant multiplier times the derivative of the function left over. So what does that mean for us? Well, it means that if I'm going to take the derivative, and here's my symbol for the action of taking a derivative of this function, I could say, you know what? What I see is I see a constant multiplier, -5. I can pull that -5 out and then just ask the question, well, what's the derivative of x to the 4th? Well, derivative of x to the 4th, we have a rule for that. It's called the power rule. The derivative of that is bring the power down and reduce the power by 1. Or when I'm all said and done, how about 20x cubed is our derivative? And I didn't have to use the limit definition at all. And there's our third rule. Here's our third rule. How about our fourth rule? The sum and the difference rule. It says, let u and v be functions of x. Great, they're functions of x. All right. It says, if you take the derivative of the sum of two functions, you can think of it as the sum of the two derivatives of those functions. Right? You know what? I know it says u's and v's here. Let's do this with do this rule with f's and g's. This says the derivative of f plus g of x is the derivative of f plus the derivative of g. That's the way it looks like if I change it instead of using u's and v's. Let's prove that. The limit as h approaches 0 of f of x plus h plus g of x plus h. That's me evaluating this function at x plus h minus the quantity f of x plus g of x. And this is the function without any internal manipulations all over h. Well, let me rewrite this. I'm just going to rearrange the order in which the numerator shows up. How about f of x plus h minus f of x? And then plus, how about g of x plus h minus g of x? I can do that, right? I can distribute that negative sign across those two terms, get rid of those parentheses, and maybe you can see where I'm going with this. This fraction can be rewritten as f of x plus h minus f of x over h plus g of x plus h minus g of x all over h, taking the limit of both of those. Now, in pre-calculus, there's probably a day in which you learned about all the properties of limits, and then you probably promptly forgot them. Well, one of those properties that's real handy right now is that the limit of a sum of two things is equal to the limit of the sums of those limits. So I can replace this with f of x plus g of x minus f of x over h plus, and here's the new part, the limit as h approaches 0 of g of x plus h minus g of x all over h. And lo and behold, what do we see here? But the definition for the derivative of f. And what do we see here? But the definition of the derivative of g of x. Okay, so I started with this definition, and I end up getting exactly what I expected, the derivative of f plus the derivative of g. Now, what's the use of that? Well, it means that if I take a look at doing something like finding that derivative, I want to take the derivative of both sides of that equation. X to the fourth plus 2x squared minus 3/4 x minus 19. Now, I'm going to be really, really long-winded here. First of all, this derivative, talked about this in lecture 1, may be written as dy dx. Also may be written as y prime. Both are acceptable. Now this, do we have a rule for this expression? The answer is no. But I do have a rule that says wherever there's addition, I can break it apart. What about subtraction? Oh, I forgot to talk about the subtraction rule. Subtraction rule is also here. Ah, how different is the subtraction rule? Well, if I were to go back through here and change all of these plus signs here to minus signs, minus sign here, minus sign here, minus sign there. We end up getting the, you can see all of a sudden we end up getting the same rule with just the idea that we can break it up in subtractions and stuff. Okay, what does that mean for us? It means this expression can be thought of as the derivative of x to the fourth plus the derivative of 2x squared plus the derivative of minus the derivative of 3/4 x minus the derivative of 19. Okay, now, do we know the derivative of x to the fourth? Yeah, we have the power rule for that. That derivative is 4x cubed. Bring the power down, reduce the power by 1. Do we know the derivative of this one? Well, we do know that we can say, you can take the constant multiplier out. And the next one, you can pull the constant multiplier out of the derivative. And this one, oh, it's the derivative of a constant. That's a 0. I'm not even going to write that. Let's finish this up. I get 4x cubed plus 2 times the derivative of x squared. Well, that's another power rule. Bring the power down, reduce the power by 1. Minus 3/4. And the derivative of x. Bring the power down, reduce the power by 1. Oh, well, x to the 0th, that's just 1. So how about 4x cubed plus 4x minus 3/4? And that's our final answer. Now, what's going to happen? Are you really going to write all of these intermediate steps down all the time? The answer is no. As you feel more comfortable with these rules, you'll go ahead and say, I'm going to do the derivative of that. You know that's a constant multiplier, so that 2 gets multiplied by that 2, giving us that 4. Hey, any coefficient on front of just a plain old x, that's just going to end up being the 3/4. Any derivative of a constant turns into zeros. You're going to do this much more snappy in the end. Okay. Does the curve, blah, have any horizontal tangents? Horizontal tangents? What does that have to do with anything that we're doing? Oh, horizontal tangents. Horizontal tangents is another way of saying, is there any place where the derivative is equal to 0? Horizontal tangents are places where the tangent line slopes are 0. Well, let's go ahead and let's find out. Y prime. Let's take that derivative of that expression. Actually, I should have 2 steps. Let's take the derivative of y. Let's take the derivative of x to the fourth minus 8x squared plus 2. This is y prime. Derivative of x to the fourth, bring the power down, reduce the power by 1. Bring the power down, that gives me negative 16, reduce the power by 1, 16x. Derivative of 2 is 0. Hey, we got the derivative. Now, is there any place where that derivative is equal to 0? Maybe I'm going to have to use some algebra. How about I factor out a 4? Oh, and factor out an x, leaving me x squared minus 4. Whoa, I think that factors more fully. 4x and x minus 2 and x plus 2. And it looks like that leads me to x equals 0, x equals 2, and x equals negative 2. So looks like there's 3 horizontal tangents for that curve. Now, let's just do a quick check and see if that indeed checks out. Go to the calculator. And let me put in that original function. I think it was, I have to have a graphing page. Graphing page, I think it was x to the fourth, x to the fourth. And then what was the rest of that? X to the fourth minus 8x squared plus 2. X to the fourth minus 8x squared. What was the rest of that? Plus 2. Plus 2. Hit enter. Okay. Well, here I am at x equals 0. Sure does look like there's a horizontal tangent there. Now, I can't see what's going on there very well, but maybe if I zoom out a little bit, there we go. Okay, right there. Except there's a horizontal tangent. Could that be at x equals -2? Sure does look that way. And over here, place where there's a horizontal tangent at x equals 2, it sure does look like we found those 3 horizontal tangents. Excellent. All right. Next rule, product rule. It says let u and v be functions. And so the derivative of u times v, not plus, not minus, times v, is u times the derivative of v plus v times the derivative of u. Or as I like it better, I like it as like a mantra. First times the derivative of the second plus the second times the derivative of the first. I like that. I actually say these words every time I do this rule. All right? It says, you want to take the derivative of this? You want to take the derivative of f? Take the derivative of this expression, which can be thought of as 2 different functions of x. This is fine. You can do that. You'll get f prime. And we say first, x cubed minus 4 is what we're going to call first, times the derivative of the second. Do we know what the derivative of the x squared plus 3 is? I think so. I think it's 2x. Plus, again, we call this the second x squared plus 3. And do we know the derivative of the first? Yeah, derivative of x cubed, bring the power down, reduce the power by 1. And there we have it. And if you're being extremely conscientious, you can get rid of all the parentheses. 2x times x cubed is 2x to the 4th. 2x times minus 4 is negative 8x. And that would be plus 3x to the 4th plus 9x squared. If we then combine our like terms, we get 5x to the 4th plus 9x squared minus 8x. Now, something that you may have noticed, I did not do the proof for the product rule. And you're like, ooh, I really don't like the proofs anyway. That was great. Well, maybe. I'm just going to note that Khan Academy has a really good video on the proof of the proof of the product rule. I highly recommend that you take a look at it, especially if you're like, I'm not satisfied. Maybe he's just making that stuff up. Well, it certainly could seem that way a lot of the times when I'm talking. Okay, rule number 6, the quotient rule. Again, we've got a derivative, but this time it's a function divided by a function. And look at how messy this symbol is. You can look at that. I'd rather have you, again, memorize it using words. It is the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. Let's see this in action. Let me take the derivative of f of x. Let me take the derivative of x cubed minus 4 over x squared plus 3. All right, I know the derivative of this is x prime, and now I'm going to speak this out. Let's start with bottom times the derivative of the top. Right? Bottom is x squared plus 3. Derivative of the top is the derivative of x cubed minus 4, which is 3x squared. Okay. Then, switching color, minus sign in there, switching color, pink. Top times the derivative of the bottom. Okay. Top, x cubed minus 4. Notice how I'm leaving that top inside parentheses. Times the derivative of the bottom, which is 2x. And then changing color one more time. Let's go with how about a green? All divided by the bottom squared. All divided by the bottom, which was 2 x squared plus 3. And we're going to square that. And there's our derivative. Now, you may feel like you don't like to leave it in that way. Maybe you want to get rid of all those parentheses, see if it cleans up okay. Let's take this part, we'll clean this up first. 3x to the 4th plus 9x squared minus the quantity, 2x to the 4th minus 8x, all over. I'll tell you, I will not be expanding out that bottom. I could, but I'm not gonna. 3x to the 4th minus 2x to the 4th, that's just x to the 4th. 9 plus 9x squared plus 8x, all over x squared plus 3 squared. And that's a fine way to leave that. And that's the quotient rule. So far we've learned the constant multiplier rule, the power rule for positive integer powers, the addition and subtraction rule, the product rule, and the quotient. Okay. But now, rule number 7, the power rule for negative integers of powers of x. It says, hey, we have something that looks like a power, but now that power is negative, like -1 or -2 or -3. And it says, even though it's negative, we use the same rule. Now, why do we need to treat this differently than the rule that we already proved? Well, specifically, we use the binomial theorem to expand out that positive integer. But this one, by its definition, is using a negative integer. But it just so happens that we have some tools that we can use. For example, let's say I'm taking the derivative of x to the nth. Okay, and remember, n is integer and it's negative. Like x to the -3. Well, you know what? X to the -3 is equal to 1 over 3. Sorry, 1 over x cubed. Yep. Well, if I write it this way, it looks a lot like I have something that looks like a quotient rule. Maybe I can rewrite this. X to the nth, but now I'm going to say 1 over x, and here's tricky, to the negative nth. Remember, n was originally negative. Negative n is now positive. Okay. In fact, how about we do something? Let's make a little substitution here. Let's let m equal -n. Just to make things clear, to make things easier. The derivative with respect to x of 1 over x to the nth. Okay, and m, by the way, must be positive. Right? N was negative. Negative n must be positive, therefore m must be positive. And now we can use the old power rule and the quotient rule combined together. Quotient rule, bottom, x to the nth, times the derivative of the top. Well, top is 1, which is a constant, 0, minus the top, which is 1, times the derivative of the bottom. Well, the power rule says we can bring down the power and reduce the power by 1. And then this is all over the bottom squared. There's me doing the quotient rule all over this. And what do we see when I clean this up? Negative m. And I've got an x to the m minus 1 on top and then x to the 2m on the bottom. That's a mess. Wait. Negative m. But m is negative n. That means negative m is just n. I'm going to replace that negative m with an n. That's one thing. Second thing I'm going to do, I've got two like bases being divided by each other. I can take their exponents, m minus 1, and subtract them, minus 2m. Get n, okay? And what is m minus 2m? Well, that looks like negative m. M minus 2m is negative m minus 1. Oh, wait, but negative m is n. Oops, got the x there. X to the n minus 1. And that's exactly what we wanted to show. So we've now proved that you can do things like do problems. Oh, like this one. Y is 1 over x. Instead of doing the quotient rule on that, we could just say that's y to the negative, y is equal to x to the negative 1. Because it's easy to take the derivative of both sides of that equation. There's y prime. Bring the power down. Reduce the power by 1. The number lower than negative 1 is negative 2. And I get negative 1 over x squared. And there's our derivative. All right, great. We've now found the derivative for this curve. Oh, we should have read the directions. Find the equation of the line tangent. Well, line tangent, what do we know? We know at the point of tangency, the derivative gives us the slope of that line. Y prime at 1 is going to give me the slope of the tangent line to that curve at that point. Y prime at 1 is negative over 1 squared. It's negative 1. Does that look like a slope of negative 1 to you? Does to me. All right. Second, we need not only the slope, but we need the equation of that line tangent. Now, I want you to put into your memory banks, whenever we're asked about a tangent line, we need two things. We need a slope and we need a point. We found the slope. It was 1. Do we know a point? Oh, they gave us a point, 1 comma 1. Now, I'm going to write this in black to make it stand out. I would like you to use the point slope form for writing lines, which is y equals y1 plus slope times x minus x1. I know. You don't want to do this. I know. You love the slope-intercept form. I understand. Happens every year. I'm asking you, force yourself to use this form. Why? Because writing the answer to the question, y1, that's that 1, plus the slope, that's that negative 1, times x minus x1. There. All right, there we got it. Y is equal to 1 minus x minus 1. I didn't have to do multiple steps. I didn't have to solve for b. And most importantly, I didn't make a mistake while trying to do any of that hard work. All right, so there we go. And what I'm saying is, if I put that equation into the graphing window, I'll see that tangent. You know what? Why not? Why not? Let's just do that. Here we go. I'm going to get rid of the earlier work. I'm going to start a new graph. I think our function was 1 over x. Yep, that looks like that hyperbola. And if I hit tab, I can put in another one. What do we say? 1 minus quantity x minus 1. And indeed, look at that, so beautiful. We can see the curve, and we can see how that tangent line just kisses the curve. Beautiful thing of beauty. All right. All right. Last part of this lecture. Everything we've been doing having to do with all these rules, I talk about taking a function and finding a derivative. Well, when we find that derivative, we have a special name. We call it the first derivative. But if you take the derivative of a derivative, you get something even more interesting. You get what's referred to as the second derivative. You can find the derivative of y prime, and you get y double prime. The action of taking the derivative of the derivative. Now, I wanted to go back in time for a second to our first lecture. This is a symbol for the action of taking a derivative. This is the noun of the derivative. I want you to know, taking the derivative of a derivative, how many d's you have? You have 2 d's. Ah, that's why there's a 2 there. How many dx's do you have? You have 2 dx's. That's why it's dx squared. It's a really strange notation, but if it's helpful, this is, again, a symbol which is equivalent to y double prime, the second derivative of y with respect to x. And of course, as you can see further in the notes, there's no reason why we have to stop there. You can also take the derivative of a second derivative, and you get what's referred to as the third derivative. And there's that function, that funny notation. Now, once we get up to 3, it starts getting hard using this prime notation that we're seeing right there. So you might see also in the book y parenthesis superscript n, end parenthesis. And we do that if I want to talk about the 7th derivative or the 9th derivative, right? It's awkward. When we use parentheses, we're talking about derivatives. When we don't have a parenthesis, we're talking about powers. All right, let's finish this off. Hey, let's find that second derivative of this expression. What happens if I'm not writing? Take the derivative of y. Take the derivative of 4x cubed. I take the derivative of y, I get y prime. I take the derivative of this, bring the power down, 12x squared. What happens when I take the derivative of y prime? Of course, whatever I do to one side of the equation, I need to do the other. Derivative of 12x squared. This is my y double prime. This is my 24x. Oh, I'm sorry. It said define that. Well, let's just remind ourselves, when I take the derivative of y with respect to x, I get dy dx. And when I take the derivative of dy dx, 2 d's, there's my d squared y, 2 dx's. There's my dx squared. We really don't say d squared y. We just call this the second derivative of y with respect to x. And there we go. There's the end of those notes.